Okay, a canning company claims they are giving the consumer 12 ounces of pop on average in their cans. A consumer advocate wants to test this claim. A sample of 30 cans is taken, and the average on the sample is 11.93 ounces. The standard deviation of the population is assumed as 0.2 ounces. We're going to check the validity of this claim and run a hypothesis test. The first step is to set up the null and alternative hypotheses. The null hypothesis is based on the fact that we will assume that the canning company is true to their claim that the average amount is at least 12 ounces in the cans. The alternative hypothesis is that it's not, that it's less. Also keep in mind that the person running the test is a consumer advocate, so if the cans are overfilled a little bit, that's not a problem. The company is actually giving more than what they claim to the consumer. The person running the test is only concerned if they are underfilling the cans, so they will go ahead and assume that there's at least 12 ounces in a can. Now, first thing we need to do is to make sure we understand what the population is. Some research would be done in determining all the stores that this canning company delivers to, and a method would be devised to go out into those stores and collect a random sample, a subset, a small subset of all the cans out there. And in this particular case, a random sample of size 30 was taken, and an average on the sample was calculated at 11.93 ounces. Step 2 is to look at the sampling distribution. We are taking sample averages, and we want to see, if we assume that the null hypothesis is true, we want to see where those sample averages should fall. They will fall normally around the 12, the claim 12, if the null hypothesis is true, and the standard deviation of that sampling distribution is called standard error. In this case, it's based on a planning value or a strong estimate for the population standard deviation, and we take that value and divide by the square root of 30 to get 0.0365. So there's our measure of variation. Now the level of significance is 0.05. Notice that any sample average above 12 would actually support the null hypothesis, and there's no reason to run the test. So we're on the lower end, and we're going to take a little bit of risk at a 0.05 level and create a decision line. Now this decision line, using the table in the book, has a z-score of negative 1.645, and that's our critical value. So if our sample average of 11.93 is to the left of this decision line, then it's far enough away from the 12 ounces that are claimed in the null hypothesis that we can reject the null hypothesis. If the 11.93 ounces is between that critical line and the 12, then it's too close to call, and we will not have enough evidence to reject the null hypothesis. What side of that decision line is the 11.93 ounces? All we need to do is to calculate its z-score, also called the test statistic, and compare it to the critical value. If that test statistic is less than negative 1.645, then we'll reject the null hypothesis. So step 3, we'll go ahead and write that rejection rule. We'll reject H sub 0 if the z-score of the 11.93, called the test statistic, is less than negative 1.645. And to go ahead then and calculate that test statistic, I'm going to take the z-score of the 11.93, subtract what's assumed to be the average, and divide it by the standard error, and I get a negative 1.92. So step 5, to draw our conclusion, we're going to reject h sub 0 since the negative 1.92 is less than a negative 1.645. In other words, we're far enough away from that claimed value of 12 ounces that we have strong evidence we can reject the null hypothesis. And the conclusion is the company is underfilling the cans. So we actually have proof, statistical proof, significant evidence to show that the alternative is true. We were able to reject the null hypothesis. It's a 5-step hypothesis test. First step is to set up the null and alternative hypothesis based on the context of the problem. Number 2 is the sampling distribution, calculating the standard error and the critical value and deciding where that critical value is going to be. Step 3 is a rejection rule, comparing the critical value and the test statistic, the two z-scores there. In step 4, we can make a decision and conclusion. Okay, running the test using a p-value, I would set up the null and alternative hypotheses as we did before. And then my rejection rule would be reject h sub 0 if p is less than 0.05. Now, the p-value that I'm looking for is associated with the 11.93. So if I look at the test statistic for the 11.93, I've already calculated that. As a negative 1.92. That being less than the negative 1.645 critical value means that the 11.93 was to the left of the decision line here. And you can see in the sampling distribution, the p-value then is going to be to the left of that z-score, or the 11.93. Now to calculate that value, use the test statistic. I look up the test statistic in the table and find the area to the left. And the p-value is 0.0274. That's the probability of getting anything less likely than the 11.93 when or if the 12 is the actual population average. And that's pretty small. So in running the test there, I have 0.0274 is less than 0.05, and reject h sub 0, and draw the same conclusion. The company is underfilling the cans. One advantage of the p-value is, again, it's the probability of getting anything less likely than the 11.93 if the 12 ounces is the actual average. So it gives us a little bit better approximation to the risk that we're taking when we reject the null hypothesis. Notice that we were willing to take a 5% risk, but in reality, based on our sample, we're only taking a 2.74% probability risk. So the chances of making a type 1 error are a little less likely than what we were requiring to do it.